So the last unit we finished about sound was all about sound waves. We're going to continue our study of waves, but now we're going to focus on light. And there are some things about sound waves and light waves that they have in common, and obviously there are some things that are different about them, huh? Okay, so the first thing we're going to do is fill in this page 1 together, and then page 2 is like questions as a review from the information that I give you on page 1. So I want you to ask yourself this. You know, I've drawn a wave for you before and asked you to label parts of it. What were some of those parts of a wave that we measured? Yeah, we did do pitch, but that's going to show up as an experience as opposed to an actual property in a wave. Frequency, wavelength. These are properties of waves. Volume is part of our experience. Amplitude is a property of a wave, right? Okay? So, I'm going to use a pretty big font here. I suggest you use a smaller one. And our first property is going to be the amplitude of the wave.
What charger?
The next property is going to be the wavelength. These are all different aspects of a wave that we can measure, and we find them in both sound waves and light waves. Next, we have frequency. Oops, not frequency. Frequency. And the last one that we can measure on a wave, the last property we can measure, is the wave velocity. How fast that wave is moving. All right, so everybody doing okay? We got those?
Yeah.
4 properties that we're going to look at. Okay? All right, what is the symbol for amplitude? What would you expect? Yeah, it's amplitude. It's A. What is the symbol for wavelength?
W.
You would think so, huh?
L.
You would think so.
N.
Well, it is the length of a wave, so we're going to look at the letter L. But we use L for length, regular length. So to mean wavelength, we're going to switch to the Greek alphabet again. And we're going to use the Greek letter for L, which is called lambda. So here's how you find lambda. There's 2 things you can do. Ideally, you go to your font and you change your font to symbol. It's in alphabetical order. Scroll way down there, find symbol. And this will give you all the Greek letters in symbol. And you want to just hit the letter L for lambda.
Uppercase or lowercase?
That's a really good question. Here is a capital lambda. It looks different than the lowercase lambda, doesn't it? Capital lambda looks like an upside down V. But we're not going to use capital lambda. We're going to use lowercase lambda.
Unless it's like a regular L.
It should be in the symbol font.
Oh, upside down. I don't have this one.
So the other thing that you can do if you don't have the symbol font is you can draw a lambda. If you need to do that, I like to draw the right side first and then the left side. Oh, yeah, you could look it up online somewhere and then copy paste that. Huh?
Maybe you probably do a Y too. You split that shit out.
Draw a little dinosaur.
Yeah. Okay, what do you think? What abbreviation are we going to use for frequency? We use F for frequency. I think it's usually a lowercase f.
Are we still on Greek alphabet?
Oh, I'm sorry. That is still Greek alphabet, huh? That's the Greek letter phi. So I forgot. I have to change this back to the normal alphabet, don't I?
Oh, that's
Alpha would be A. And velocity is V. Usually it's going to be a lowercase. I think for velocity it doesn't matter so much.
Is it A uppercase or lowercase?
I like to use the uppercase for amplitude. Everybody got the symbols?
Hey, how do I get that Greek symbol?
You gotta go to your font up here. Gotta open the font, pull down the list of fonts, scroll down to symbol. Symbol font. It will actually be spelled SYM, symbol, because you're using these symbols instead of letters. Now, what is the amplitude measure? Is that from the top to the bottom of the wave or from one wave to the next? What's amplitude? Yeah, it's top to bottom of the wave, isn't it? In other words, it's the height of the wave. What about wavelength? Where's wavelength?
The length of the wave.
It is. It's measured in centimeters. It's measured in millimeters and meters. It is the length from one peak of a wave to the next. In fact, it's shown right down here, isn't it? The wavelength is from, I guess we're going to say distance. See how I'm trying to avoid the word length in there? How's that? Distance covered by one wave. In other words, the length of the wave. I'd rather you avoid using a word in its own definition. That's what I'm trying to do. So I'm using the word distance instead of the word length. The frequency. This is the number of waves in usually 1 second. Although we could measure frequency in different time periods, but frequency is about measuring time. What about velocity? What do you think that means? How fast it's moving in a specific direction, huh? Right? So this is not how fast the waves are going up and down. It's how long the wave takes to go from the speaker to your ear. Or the light wave, how long does it take to go from the sun to your eye? It is an actual speed measured as any other velocity would be in meters per second. It's the time for a wave to cover a distance, how fast it's moving. Just like any other speed is the time it takes for something to cover a distance, right? If you're going 60 miles an hour, it takes an hour to cover a distance of 60 miles, right?
Isn't it like if the sun blew up right now, we wouldn't see it until like tomorrow or something?
We're gonna actually calculate that. You're on the right track. We're gonna calculate how long that would be in just a few minutes. So where this says compares, what we want to do is fill in some phrases that describe different aspects of the property. So for height of a wave, I might say it's taller or shorter. Does that make sense? For amplitude, I could say it as a taller amplitude or a shorter amplitude. But that means I want to avoid using taller or shorter for any other comparison, huh? So that we can have a common language here. What about wavelength? What could we say about that? Well, I could say longer and shorter, huh? But didn't I already say shorter over here? How else could I describe something besides using the word shorter?
Bigger,
And we could use big and small.
longer.
What about wider versus thinner or narrower? Whoops. Not cider. Wider. I used the right finger, but I didn't hit the right key. What about frequency? That's how many waves per second, right? How could I describe that? A lot of waves per second versus not very many. How could I describe that? So what would I say? I might say faster or slower, except wouldn't that be better for velocity? In fact, let's fill that in for velocity right now. Faster or slower? I think we should say more or less. Yeah. Or we could say many versus few or something. We could say high versus low for frequency too, couldn't we? In fact, that's a common word. I'm going to go with higher or lower. We'll talk about high frequency and low frequency sound, high frequency and low frequency light waves. So I think those are a better choice to stick with that. Faster or slower is for velocity. Which is faster, speed of sound or speed of light? Light is so much faster, and we're going to look at that in a second. So for example, let's say you're at a football game, and on the other side of the field, there's a guy with a bass drum. When you see him hit the drum, do you hear the sound at the same time? He's on the other side of the field. He's 100 yards away. You see him move, right? And then later you hear the sound. Are you with me? So which has a faster velocity? Light. Light is so fast that it's almost instantaneous. You see him hit the drum at the moment he hits the drum. But then there's a delay for the sound to get to you, huh? We calculated what that delay was for lightning, remember? If you count to 5, that means the lightning was, you saw a flash, you count to 5, you hear the thunder. That means the lightning is a mile away. I think it's pretty useful information if you're ever like out hiking on top of a mountain. There's a lightning storm. You want to know how close that stuff is. Well, check this out. If we look at the speed of light and if we look at the speed of sound, we can see that there's a big difference between them. Light. Sorry about that. So light has a velocity of 186,000 miles per second. Per second. Sound has a velocity of 750 miles per hour. See the difference? Now check this out. If this is the Earth, the equator is about 25,000 miles going around the Earth. 25,000 miles at the equator. How many times could light circle the Earth in 1 second? If you set up a bunch of mirrors, couldn't you bounce a light wave around the Earth? Well, wait a second. It's 186,000. This is only 25,000. Light could circle the Earth about 7 times in 1 second. That's a lot of times. That's how fast it is. But wait a minute. Let's see. The sun is 93 million miles away from us. Get out your calculator. Sun is 93 million miles away. Moon is only 1/4 of a million. So this is what I want you to do. You see this, the velocity for light up there? 186,000 MPS, miles per second. Put that in your calculator. 186,000. But that's miles per second. We need to change that to miles per minute. How are we going to do that? Multiply by 60. What do you get if you multiply by 60?
11,160,000.
11,160,000.
Yeah.
Now it's MPM, miles per minute, correct? Now, wait. Remember that number, or you can look up here again in a minute. You have to clear your calculator, put 93 million into there. Put 93 million in your calculator. Now divide by the speed of light per minute. 11,160,000. Yes, 93 million divided by 11 million and something. That's the number of minutes it takes for light to reach you, to reach the Earth from the sun.
I told you it was about 8.
You're right. So what does that mean? If the sun went out right now, would you know it? When you look at the sun, are you looking at it the way it looks now? Or are you looking at it the way it looked 8 minutes ago? You're seeing 8 minutes in the past when you look at the sun. If the sun went out now, when would we find out? 8 minutes later, it would get really dark and really cold really fast. Right? Yeah. Well, the problem is that there's nothing faster than the speed of light, so they couldn't detect it except at the speed of light, which says it's going to take 8 minutes for any information to get to us. So I don't think we would. Unless we knew for some reason that it was going to happen. If we had a sensor closer, yeah. If we had a satellite closer, except wait a minute, that satellite sends us a radio signal which travels at the speed of light. Radio waves are a type of light. They travel at this same speed, 93 million miles, 186,000 miles per second. So I don't think we would know in advance. What about this? If it takes 8 minutes for us to see what the sun is like, what does it mean when somebody says, oh, that star is 100 light years away? That's correct. It takes 100 years for the light to get to us from that star. So when you look at that star, are you seeing it as it is now? You're seeing it as it was 100 years ago. Now let's turn that around. What if there's some civilization on that star or on a planet orbiting that star, and they have a really powerful telescope that is looking at us, but they're 100 light years away from us? What do they see? They see 1922. Right? If they're looking at us from 100 light years away, they're seeing what we were like 100 years ago. What if we're 100 million light years away?
How does that make sense though? Wait, our Earth.
Because the light that was released from 1922.
But they're not going to see like tanks and war happening.
Well, let's just say they had some super kind of telescope where they could see that.
That's
It doesn't exist. You're right.
fictional.
We don't have it.
That's fictional. No, it's never going to be possible.
It's a hypothetical.
We're all the time, we are improving our technology so we get more and more detail, aren't we? We just sent out a new telescope into space that's going to give us more information. So, Right now it is fiction, but it's science fiction, so it's based in scientific theoretical possibilities. So let's back up to 100 million years ago. If some civilization on a star that was 100 million light years away, and they looked at us, what would they see?
World War II and all the tanks.
100 million years ago,
Yo!
They would
World
see-
War I.
they would see dinosaurs.
Those didn't exist.
100 million years ago, they did. So the further away you go, the further back in time you're able to see.
Yo, let's do it.
So when we look at these stars and galaxies that are 100 million light years away, are we looking at them as they are now? Or are we looking at them as they were that long ago?
Maybe there's aliens.
In a way, are we able to time travel? In a way, we are time traveling by looking at what the universe was like that long ago. But only kind of, it's not like we're able to go there, right? Okay, brother, you are an idiot, bro.
Mr. Fairley,
Nope, not right now. So, we're cutting way back on our bathroom passes. We've had too much free bathroom and it's not gonna happen. Oh, well, you better go to the bathroom before the bell rings. That's all I have to say, because we're not going as much as we have been nearly.
that was like an hour ago.
So, how do you and I experience changes in amplitude? We do. It's called volume, right? That's for sound waves. How would we experience it for light waves? Exactly. Brighter versus dimmer. So for our experience, we either have loud versus quiet, or we have bright versus dim, depending on if it's a light wave or a sound wave. Okay? How do you and I experience changes in the wavelength of a wave? No. Sorry? It's really closely related to music.
Oh, notes.
Pitch. That's true for sound. How do we experience changes in wavelength for light? Like if and brighter and darker is amplitude. So what happens to light if I change from this wave to this wave? We have changes in color. So when we change the wavelength, we either hear a different pitch, or we hear, or for visible, for light, we have changes in color.
So would we go different pitch or color, not pitch or color?
Well, this could be high or low pitch, and this could be different colors.
So you just want us to put pitch or color?
Yeah, depending on what I'm saying here, just like loud, quiet, or bright, dim. Okay? I could have just said volume versus brightness, volume or brightness. So wait a minute, what's the next one? Frequency? Didn't we say that frequency and wavelength change together? When one goes up, the other goes down. So check it out, watch my hand. Is this a long or a short wavelength compared to this? First one was long, right? Long wavelength. What was the frequency? Count how many waves I just drew in the air. 1, 2. What's the frequency now? 1, 2, 3, 4. What happens as the wavelength gets shorter, the frequency gets higher. So these are connected together, aren't they? Doesn't that mean if I change the pitch of the wavelength, I'm also changing the pitch of the frequency at the same time? Because they are totally connected to one another. You can't separate wavelength from frequency. They're different measures, but one is connected to the other. You can measure them separately, but if you change one, you will change the other. When one increases, the other decreases. What kind of relationship do we call that? inverse relationship, right? When one goes up, one goes down. Finally, velocity, this is where it's just the speed of light versus the speed of sound. So maybe for this one where it said experience, I should have described it as seeing something before you hear it, right? Thunder and lightning getting separated like that. Okay, this is what I would like you to do. Where it says measuring wave properties, there's 4 of them to read about. I would just like you to turn to your neighbor and go over those 4 with each other. Right? Those
Over
four.
these four.
Yeah, no, below that where it says measuring wave properties, it gives definition of those 4 properties.
Are you still doing this?
Johnny's getting excited.
I'm good. There's no better warriors.
Did we go over those 4? Okay, first thing I want you to do, when it talked about a peak, there's another word that means the same thing. A peak of a wave is sometimes also called the crest. So add that on there. The peak is the crest. And then let's add an arrow pointing to one of these peaks. The top of the wave is the crest, also known as the peak. Is that good? Now this next one, sometimes people get confused by this word. It's one of those strange words that ends with GH, but you pronounce it like F, just like laugh. And this is a trough. And I think it's named after, like, think about a farm where the horses come get a drink out of a trough, right? You know what I'm talking about? You know, or you can grow plants in a trough, yeah. So wouldn't that be the lowest point on the wave? Or the dip, yeah, but I don't think this one, the trough itself only has this one name.
It's literally just a crest, but upside.
So what I'm going to do is I'm going to draw another arrow pointing at the trough, and I'm going to label it as the trough. Sorry? You can draw them, but you can get them out of the shapes also. Are we good on the difference between a crest, a peak, and a trough?
Wait,
There's no difference between
isn't a crest and a peak the same
a
thing?
peak and a crest are the same thing, right? So maybe I should have rephrased that. Do we all understand the uses of these terms, crest, peak, and trough? Right? The crest or the peak is the high point of the wave. The trough is the low point of the wave. Okay, let's move on. We're going to, well, we've been talking about waves. It's about time we define it, don't you think?
Yep.
Yep.
It's a high point and a low point.
Okay, so there's our definition of a wave. A wave is a disturbance. That's what it is. Like, am I disturbing the air molecules by speaking?
Yeah.
Yeah, I'm probably disturbing your brain a little bit too. But a wave is a disturbance. And what that disturbance is doing is sending energy from one place to another. So my voice, those sound waves carry energy from my vocal cords to your ear, huh? Right? It's actually carrying energy. And it has to have a material to transfer through. And the material that is carrying that energy is called the medium. So that's where this definition comes from. A disturbance that transfers energy through a medium.
Right,
And
how
a
do,
medium
like,
is just a material.
how do speakers know what waves like?
Yeah, so in the speaker, they have the wires that come in the back, and those electronic wires give a signal to the speaker of how to vibrate. On the outside of the speaker is where it's able to vibrate slowly, and those would make which tones? The low tones in the woofer, right? They call it the woofer. And then in the center, or maybe separately, they have another part that vibrates very quickly for the high tones, the tweeter. If it's a separate unit, they call it the woofer and the tweeter. And that's why they call it a subwoofer, because it's really low tones.
It's weird that like
That it's vibrating at exactly 440 hertz. Yeah. Yeah. So technology's nice, huh? Okay, next. There are two kinds of waves. Please look on the worksheet. What are the names of those two types of waves? Transverse wave and longitudinal wave. And notice that they differ by the way that the disturbance was moving. You see that? They differ by the way the disturbance moved. So, what we're going to do is we're going to put some arrows on here. And we need two different kinds of arrows. One to show the movement of the wave, like from my vocal cords to your ears. So I'm just going to make a key down here, and I'm just going to use a regular arrow for that, showing that the wave is moving from one place to another.
wait, so there's like throat just
Yes, our vocal cords, we have amazing control over these tendons that rapidly change how much tension is in this vibrating cartilage. And that can vibrate in a couple different places at once. And you learn over time how to control those vibrations. A singer really learns how to control those vibrations.
that's
So what I want you to do is draw an arrow here, and then I want you to copy and paste it twice. Remember Control C or Command C to copy, Control V or Command V to paste.
Like, how many arrows are we drawing?
3. You drew one, and then you copied and pasted it twice. So, do you see what I have done there? I have shown the wave moving from left to right, correct? Both of these waves, both the transverse wave and the longitudinal wave, are moving from left to right.
Can we just leave the first arrow on the
I'll hold on to it till the end of class, then you can have it back. Don't forget. Are we good? So the wave is moving from left to right in both cases, isn't it? Now we got to talk about these words transverse and longitudinal. Which one, like look at me, this direction compared to my body, does that seem like it would be longitudinal or transverse? It's going the same direction as my body. It's parallel with my body. It is longitudinal. If I go across, then it is transverse. So do this with me. Take your arm. Take your arm. Hold out one arm. Take your hand like it's a knife. And if you're going this direction, is that parallel or perpendicular? Parallel, is that longitudinal or transverse? Longitudinal. You know, they use these same descriptions in anatomy. Yeah, like if you were gonna dissect an animal and they said, do a longitudinal section of its arm, it would be this way. If they said, do a transverse section, it would be across, right? Right? So try that. Do the transverse movements compared to your arm, just to drill these into your head. Transverse is going across. Longitudinal is going the length, right? Transverse goes across. That means for waves that the disturbance is either going to go the same direction, parallel to the arrows we just drew, or it's going to go perpendicular to them. So this is what we're going to do. Get another arrow.
Can I just copy and paste the other one?
You can. I'm going to convert this into a dotted arrow. And the way I do that is I hit properties and I go to style and I change that to dotted. Or maybe you have a way to make a dotted line, or maybe you need to use a different color. But what I really want to do, and unfortunately the PDF isn't going to let me do it the easy way, I want a double-headed arrow. So what I'm going to do is I'm going to copy paste, and then I'm going to flip this one over so it's facing the other direction. You could do one way and one another way if you wanted, yep. And I'm going to try to come up with a double-headed arrow that looks dotted from one side to the other.
Make it super.
I like having these be dotted. They don't have to be dotted.
Oh, so you just.
I have the entire thing being dotted. Okay, so for the longitudinal wave, this is the easy one. The disturbance is in the same direction. Same direction as the wave is moving. It's parallel. So I'm going to show my disturbance that made this sound wave like that. Does that make sense? It's vibrating back and forth in the same direction as the wave. Is that okay? What about the transverse wave? What direction should it be vibrating? It should not be vibrating front and back. It should be vibrating up and down. Wouldn't that push the peak up and the trough down? So to do this one, I'm going to copy and paste those arrows once again, but I have to turn them so they're up and down. I'm going to do that over here.
Which side do we do it on?
I would do it where the disturbance began, because then that disturbance is being transferred through the material. Hold your phones? And shouldn't we just be collecting phones at the beginning of class every day?
I've seen him twice.
You see my phone twice?
Did I say you?
Yeah, you said both of us.
I said he's been on both.
Okay, let's end the argument and just put our phones away, okay? Like, put it away, out of your way, out of sight, out of mind. Okay? You guys just saw how you should behave with your phone. What did I do when the phone rang? Did I pick it up and look at it to see who it was? Or did I just reach over there and turn it off? I just turned it off. I didn't even look. Right? Because I'm busy right now. This is my focus. You are my focus. Well, you know, that's an interesting question. What if it's a hospital? Think about the days before there were cell phones. They call the front office and they send somebody up to class. Right? That's still an option today. Okay. So did we get these double-headed arrows showing the disturbance okay?
Yeah.
So the wave is moving over here, but the disturbance is doing this, isn't it? Does that seem like a sound wave to you? That would squeeze some molecules together and stretch others apart? Meanwhile, what about the light wave? Moving up and down, isn't it? Different kind of disturbance. And to show that more clearly, I want to do a little demo down the middle of the aisle of the class. So I need some help from you guys. First of all, we need all those bags removed from the aisle. And then you need to move so that you can see the floor. Come on, guys, I need these bags moved. And then, let's see, Joey's in the perfect place. You're gonna hold that on the floor. So you need to be able to see the slinky. So rearrange yourself so you can see it. Yeah, this is why we're not all doing it, because the slinkies are actually much more delicate than you can think. So can you see okay? So if I disturb the slinky from side to side, I'll be making a transverse wave, right? You see the wave hit his hand and then bounce back? Can you see the crest and the trough? Here's the other, watch really closely. If I move it to the right, what direction does it come back after it hits Joseph's hand? Exactly, it reflects back the opposite way. So this is transverse wave, isn't it? Right? But watch this. This one's a little harder to see, but check it out. Are you ready?
Yeah.
You see that wave? It's bouncing off his hand again, isn't it? This is what kind of wave? Longitudinal, right? The disturbance is going in the same direction as the slinky is, huh? It's going with the slinky instead of against the slinky. Well, let me just the floor. It's the same as side to side. But
At the same time.
3, 2, 1, go. Oh, good question. Let's do them. Yeah, do that one. 3, 2, 1, go. I think mine kind of overwhelmed yours a little bit. It's harder to see. Let's both go to the right. 3, 2, 1, go. They canceled each other out when they got together, didn't they? 3, 2, 1, go. Oops, I went early. Sorry. 3, 2, 1. Like a quick draw. 3, 2, 1, go. So they kind of cancel each other out when they bump into each other, don't they?
Yeah.
All right. Did you guys see okay in the back? Yeah. Yeah? Okay. So the idea there was so you could see the difference between the transverse and the longitudinal wave, right? That was the plan. Let's go on to page 2.
Hey, yo, waves properties.
Isn't that the perfect font? Okay, here's the sound wave, right?
So that's what they actually look like?
This is much better than what I've been drawing with the parentheses. Because what do you think every one of these little dots is? Every dot is a different molecule. And does the wave squeeze some molecules together and stretch others apart? Right? So let's see, can we label anything on here yet? What do we call it when they're squeezed together? Where is the zone of compression?
On the second bracket.
You say it's the second bracket?
Yes.
Tell me why you say that.
Because all of them are super compressed.
All of them are squeezed, huh? Well, it's kind of hard to label that. So you might want to put ZC, but I think over on the side, you should probably make a key that explains the abbreviations you're using. Zone of compression. So you should do that on, did we say the second bracket? Does that seem right? What's the opposite of the zone of compression? ZR, the zone of rarefaction. Yeah. Do you see how many air molecules are squeezed together here?
Yeah.
How many are there? A lot fewer, right? Are they more rare?
Yeah.
They have been rarefied. It's kind of like you could think of it as thinning out. They have been rarefied. As you go higher up on the mountain, the air becomes rarefied. There's fewer molecules for you to breathe. So that's where this word is coming from, rarefaction. So which bracket should be the zone of rarefaction?
Third.
The third one, it's only rarefied. Second one, only compressed, correct? What does that mean for the first bracket though?
Cumberefaction. It's full.
Rare pressure?
Yeah. Rare
The
pressure.
first wave includes both a compression and a rarefaction, doesn't it? But then another zone of compression starts. Wouldn't this be a second wave right here?
Yeah, but it-
Wouldn't that be like kind of like keep counting from peak to peak? So isn't this actually the first bracket showing one wave,
Yeah.
a single wave? And it's measuring the distance from the beginning of the ZC to the beginning of the next ZC. If I'm measuring a distance, what is it? It's wavelength,
Oh, shoot.
right? So you can either spell out wavelength or you can use the Greek letter lambda. Yeah. What is theta? Well, the way you draw it is like this. It's kind of a TH, so it doesn't completely translate to an English letter. So we have more letters than the Greek alphabet does, first of all, and some of them are a little different than ours. The sounds that they make, yeah. We have some, I think, wasted letters. We have extra letters we don't need. We don't need the letter C. Because everything either makes a K sound or it makes an S sound. Right? So like we could spell Mr. Pollard's name would be Kash and it would sound the same, right?
Cash.
All right, what's next? Okay, we did these three brackets, correct? What about this bracket showing how tall it is? Not frequency. What do we measure with how tall it is? We measure the amplitude. So this bracket that is showing how tall the wave is, we're going to label that amplitude. And what was frequency? That was the number of waves in 1 second, huh? If this took 1 second to go from the speaker to the ear, the frequency, you have to count how many waves there are, correct? And the easy way to do that is to count how many zones of compression there are.
6. Sorry. That's what I
So
said,
go
too.
ahead, fill in the frequency, count your waves.
What's frequency measured by? Hertz, bro.
Yeah, and the unit we use to measure frequency is hertz, abbreviated HZ. It is capital H, lowercase z, because it's named after a scientist who spelled his name like this. So he took the first and last letters of his name, kept the capital letter at the beginning. You know what it is, but I don't think they have the T in it. Am I right about that? Maybe they do have the T in it. Do they? So it's not an uncommon name.
That's mine.
Okay, next. What is the direction of the disturbance in a sound wave? Is it parallel or perpendicular? Maybe we should refer back to this that described them, huh?
Wait, are we measuring this?
We're looking at the disturbance. So which was the sound wave? Was this the sound wave or was this the sound wave? This one was, wasn't it? What direction is the disturbance? Parallel or perpendicular? So the answer I'm looking for on direction of disturbance is either parallel or perpendicular. Which way was this disturbance created to make a sound wave? Was it in the same direction or across the movement of the wave?
It's going from his mouth to the ear. The speaker to the ear.
Yeah, yeah. In the same direction as the sound wave is traveling, huh? It's vibrating like this as it goes. It's not doing this. Only once this week. Is today the only time? You're gonna stay in class Thursday. So what's our direction of disturbance? Parallel or perpendicular? I don't know. It seems like I've got some people with me and other people I've lost.
I'm saying parallel.
So direction of disturbance, you have two choices, parallel or perpendicular. Anything else is not going to be correct. Then underneath there, it says type of wave. Now, what do we call that kind of wave that is created by a parallel disturbance? If you need to, scroll up to page 1 to review. And what's an example of this kind of wave? Well, it should be pretty obvious from this diagram. The example is sound. Now I want you to do the same thing yourself. We just did that.
Wait, type of wave, what was that?
There's two types of waves that are shown up here. What are the two types of waves? Yes, that's one type, and the other is? And so you have to choose which one this is.
It's longitudinal.
Absolutely. Now the next wave that goes up and down, what color is it? Kind of greenish. You're going to do that one on your own. You're going to answer the question underneath there. You need to save your work. You need to turn it in. Oh, the very last question I'm going to help you with.
Wait, what's the example? The example part?
I appreciate you. Like this one, this is velocity, so the unit must be.
Yeah, the same thing. Yeah.
So answer the question, label the part, label the second wave. Answer the questions at the bottom. If you need help with that last question, I'll help you, but it's a simple math problem. The numbers are not simple, but the math is simple.
For this one, do we count like the amount of crests for?
Yeah, and if you count the number of troughs, you should get the same answer, right? Although it kind of depends where you.
Do we still use it in hertz even though it's light or whatever?
Frequency is also hertz.
Sound and sound. You get? Over.
The whole story. Only once this week. I believe it. I haven't done the math, but I've seen people get that same answer before.
Hey, I'm all done.
And then I just turned it in. I just turned it in.
Yeah. You finished? What'd you get on that?
That arrow, Cole.
There's still one more. All right, if you weren't sure how to do that last question, it gives you a frequency and it gives you a wavelength, and it's asking for how fast it is. If you go back to the first page, you're going to find an equation for velocity of a wave. How fast it is. The velocity is its frequency times lambda, F lambda, frequency times wavelength. So all you have to do is take those two numbers and multiply them, right? Yeah. Save your work, turn it in, just frequency times wavelength.
Nah, I got you. Did I ask you?
Yo, Sam, want me?
Oh, yeah. Can I go fill this up?
Yeah.
Is
Wait.
it still measuring meters per
Yep.
second?
He wants to go fill up water.
Or can I just fill it? Or is this water clean?
It is.
Or
It's Tahoe water. It is all Tahoe water, yeah. I think I heard somebody asking what unit that would be. Since it's velocity, it's just the same as velocity ever is, right? What unit is that? What unit do we measure velocity? Meters per second.
oh, I don't know if that's so full of water or not. Oh.
Sure, I'm.
Dude, who the fuck is Jordan Mouthful?